Today, I want to look at how we can program the method of bisection and also Newton's method. I'm going to proceed in a very cautious, stepwise manner, making sure I haven't made any typos as I go along. So, to get started, I'll create a file called bisect.f90. I'm running things from the command line. You may be using a GUI, but the Fortran is the same either way. This program does nothing. I've saved it. I'll go out to my operating system. It compiles. It runs, but of course, it doesn't do anything yet. So I'll go back into my program and I'm going to have to make some declarations. What am I going to need to do bisection? I'll need the left end of the interval, which I'll call A, the right end, B. I'm going to be computing midpoints. I'm going to be using function values, so I'll at the very least need these things. Colon, colon. I need A, B, M, and F at the least. Also, I'm going to do things in a loop, so I'm going to need an integer as a loop counter. How I deal with the calculation of the function values, we could do this a couple of different ways. I think what I'm going to do is I'm going to go on and have a separate program unit, a function named f. We'll put that in shortly. I have to set the initial values of a and b. I'm going to do as we did in the classroom discussion. I'll set a equal to 1 and b equal to 2. I'll use the same function that we were using previously. So I'm going to have a loop. Do I equals 1 comma. For purposes of illustration, I'll just do 10 steps of this. There has to be an end to do to go with it. I'm going to do this in the most simple-minded way I can think of. There are objections to what I'm about to do, but we'll talk about that in our next class meeting. Firstly, I'm going to calculate the midpoint. A plus b over 2. Now, I'm going to discount the possibility, at the moment at least, that I've landed on the answer. So the function value at m is either positive or negative. I've made a typo right there. I'm going to leave it so that you can see what happens here. I'm going to try to compile my program. It doesn't understand what that statement is. If you type in a whole bunch of code, probably you're going to get a whole bunch of error messages like that, and it would be difficult to track down what the problem is exactly. So I like to compile my code after 10 lines or 20 lines. This way I catch my mistakes before they turn into a big mess on them. Now, how am I going to decide about which side to throw away? I'm discounting the possibility that any of these function values are 0. That means they're positive or negative. If you multiply two numbers together and get a negative answer, that means they have opposite signs. Now, this is numerically not a very good way to do this. as we'll talk about in another time. But for purposes of illustration, we'll just do it this way. If there's going to be some condition, then, and if one thing doesn't happen, something else will. I'm going to do a terrible thing. If f of a times f of m is less than 0.0, then logically that means the function value at a and the function value at m have opposite signs, meaning that I should reduce b down to the value of m. So if that happens, I'm going to set b equal to m. If it doesn't happen, since a and b had opposite function value signs to start with, if m's function value has the same sign as f of a, it must be the opposite from f of b. So if the previous thing didn't occur, then I'll set a equal to m. This is the guts of my program here. I need to decide what I'm going to print out to. At every step of this loop, I have this if-then-else thing going on. So what I want to do still inside that loop is to print some stuff out. I'm going to print star, comma. I'm going to print a literal string that tells me what it is I'm looking at. I'm going to mention that I'm printing m and also the function value that goes with it. Now, that's a literal character string that I'm putting in here. I actually want to print out the m and the f of m as well. Now, I don't have function f built into this yet, so it's going to complain when I try to compile it, but I want to do that anyway to see if I have any typos or anything. Undefined reference to f, it yells about it quite a bit. Doesn't say anything else. So after my program, after the main body of my program, I'm going to have a real function. It's going to take variable x as its input. At the end of the function, I say end. I could say end function also if I thought it looked nicer. I have to tell it what kind of thing x is. And my function, the value is going to be sent back in this variable f. So f is going to be x to the third power minus 7.0. It should no longer complain that it doesn't know what f is now. And not only did it not complain about f, it didn't complain about anything. This executable a.out was created just a moment ago. And when I run it, I get m and f of m. If you'll look back to your notes in the in-class discussion when we were solving this problem, you'll see that the numbers that I'm getting for m are the same numbers that we were getting in our in-class discussion. The function value starts off at negative 3.625, And by the end, it's been reduced down to about 1.6 times 10 to the negative 3 power. So we have a working bisection code now. There's stuff wrong with it that need to be fixed, but it's working at least. Next, I'd like to do exactly the same kind of thing, except for Newton's method. I'll have a main program. Now, we already know that we're going to need a function f, but for Newton's method, you also have to have the derivative. We could write a routine to do both of them at once, but I think it's logically clearer if you do them separately. So my program doesn't do anything yet, but I'm going to go on and put my functions in. So my function f is the same as it was before. And then, feeling intensely lazy, I'll just make a copy of it. Of course, if I've made any typos or anything in the first one, they will be here as well. So I'll call my derivative function f prime. The derivative of x cubed minus 7 is 3 times x squared. Let's see if we made any typos here. No. Of course, the program doesn't do anything because the main program is completely empty. We need to go in and put some content in here. Now, unlike bisection, I don't have a bracket. I don't need an A and a B. I'm going to overwrite the new estimate into the old one. If I want to do something similar with Newton's method, the code is not very complicated. This time, I'm going to have two real functions, one of them f, the other will be called f prime. The first one is the function that I'm trying to find a zero of. The second one is the derivative of that function. And as we did in the class meeting the other day, I'll start x at 2. I'm going to go around and do 10 steps of this. We've talked about the do loop a couple of times before. I'm going to find the quantity x minus f of x over f prime of x and store it back into x. I'm just overwriting my computed estimates of the solution. The function is exactly as it was for bisection. The derivative of x cubed minus 7 is 3 times x squared. Very quickly, we get this number 1.91293120. We get that after about 3 steps of the method. The number never changes after that. We'll have to look into why that is, but roughly speaking, we've got as good as an answer as we're going to obtain after only about 3 or 4 steps. I wanted to make this video very simple so that you can see things are not very complicated. In Fortran, we now know how to deal with simple output. We know how to do loops. We know how to do if-then-elses. We know how to write separate function units like f and f prime. You can already do quite a lot of programming with just those elementary ideas. As we go along, we will refine our ideas, both in terms of the coding and also in terms of some of the ideas behind it. In the meantime, I wanted to get this out because I'm already running behind. I hope you have a good day. I'll talk to you again real soon.